Hi everyone, I'm Dr. Clare Gillies. I'm a medical statistician at the Leicester Real World Evidence Unit, which is based at the University of Leicester. And today I'm going to be giving an introduction to biostatistics. So what I'm hoping to cover, I'm going to start by thinking about different data types and talking about the different types of data that you might come across in research studies. I'm going to talk about the difference between populations and samples when it comes to carrying out research, differentiate between the null hypotheses and the research or alternative hypotheses. I'm going to talk about interpreting confidence intervals, effect estimates, and hypotheses to test. And I'm also going to have a bit of an overview around choosing the right test depending on the type of data or the research question that you're asking. So they're the aims. So if we start by thinking about the types of data that you're going to come across during your research career, there's broadly two main types, which are categorical or continuous data. And within those, there's a number of different subgroups. So for categorical data, what we're thinking about really is data that falls into categories. So it'll be some characteristic of a population or group that naturally falls into categories when you're describing it. So there's different types of categorical data. Binary data where you have two possible categories. So for example, a positive or a negative outcome of some sort of a test, whether individuals in your sample are alive or deceased at the end of a study, any yes/no variables. They're all binary variables where you have categories in your answer, in your response, and there's two possible options. Where you have two or more categories in your data, it can either be considered as ordinal or nominal. So for ordinal data, your categories have a natural order in them. So for example, if you're looking at severity of disease, where you classified people as being mild, moderate or severe, you can see that there's a natural order there. Severe is worse than moderate and moderate is worse than mild. And again with age groups, so you can see for the example here, you've got your groups increasing in age and there's definitely an order to those categories. For nominal data, this is where you have three or more groups and now there isn't a natural order to them. Blood phenotype is a really good example of nominal data. So depending on whether you're A, O, A, B, there's no order to those categories. Marital status is another good example. So you could categorize people as married, single, divorced or widowed, and there isn't a natural order there that you could place those categories in. So that's categorical data. The other main type of data is continuous data. So this time, instead of being able to group your sample on the outcome of interest into different groups, you've now got data that's on a continuous scale where individuals could take any value on that scale for that outcome. So good examples are things like weight and height. You could divide the scale up into categories, but normally it's measured on a continuous scale, and an individual takes one value on that scale. Again, there's different types of continuous data. So there's interval data, and for interval data, this is actually quite a rare type of continuous data, and you won't come across it very often. But for interval data, the value of 0 does not imply none. And the two common examples of interval data are temperature in degrees centigrade where 0, although it's a very cold temperature, it's not telling you that there isn't a temperature. It's not no temperature, and you can get negative values of temperature on that scale, and the pH as well. The value is 0 is doesn't imply none. Ratio is much more common type of continuous data, and it's what most of your data would be considered under. And here, the value of 0 does imply none. So, for example, if someone had a 0 value for their pulse, they'd have non-pulse. You can be 0 years of age when you haven't reached your first birthday. But you know, things like weight and height are also considered to be ratio data. The other characteristic of ratio data is that it cannot take negative values. So you can't have a negative weight or a negative height or a negative age. When you're it's important to understand what type of data you have, because that influences how you're going to summarize your data and also how you're going to analyze it. So understanding what type of data you have is really important. When it comes to summarizing categorical data, what we usually do is to look at some sort of frequency of observations in each category. So how many people had in your sample had each blood group, for example. And also we report some sort of relative frequency of the observations. So the proportion or the percentage of the total number of individuals who fell into each group. And both these numbers are really useful. So you can see here the example for the blood group. We've got the number of patients with each blood type, and we've got the percentage. And the percentage really helps you to see what proportion of individuals fell into each category. So categorical data is fairly easily reported just with numbers and percents. Continuous data, there's a number of things to think about when you want to summarize continuous data. The first of which is the shape of the data, and this then affects what you report. So you need to understand the distribution of your continuous data, and that will indicate which measure of location, which is the average value of your outcome for your sample. So which measure of central location you use and which measure of spread you use, but are both dependent on the shape of your data. So we'll talk through all these so you can see what I mean. But for shape of the data, so what we do here is plot a frequency distribution, and this helps us understand the shape of our continuous variable. So you can see here, for an example, serum cholesterol has been measured on a number of individuals in your sample of interest. And so, for example, you can see those in your sample who had a value of 5 millimoles per litre for their cholesterol. I think there was 9 individuals. So you've got serum cholesterol on your x-axis, and up on your y-axis is the number of individuals who had each of these values in your sample. So you can see, for example, those with a value of 5.5 for their serum cholesterol, it looks like there was about 17 people in your sample who took that value. And what we're looking for when we plot a frequency distribution is we're looking to see what shape this data takes. And what we really want to know is whether it follows a bell-shaped curve or not. So here's an example of a bell-shaped curve. So you can see it's lower at the tails, it goes up in the middle, it's nice and symmetrical. And when data follows this sort of shape, it can be described as normally distributed or parametric data. You never get a really nice curve such as this, so there's always a bit of subjectivity when you're trying to decide whether your data is normally distributed or not. You can do a specific statistical test to decide if your data is normally distributed, but I would usually just do a frequency plot and check by eye. And although there's a bit of a skew in this cholesterol data, so you can see there's a tail end here where there's more people with higher values, and this tail is longer than those at lower values. So there's a little bit of a skew, but overall, I would say that's fairly normally distributed, and I would be happy to treat that as parametric data. Here's some examples of skewed data. So you can see here where you've got values, you've got a tail that points towards positive values on the x-axis. This is called positively skewed data. Where the tail goes in the other direction and it's pointing towards negative values on the x-axis, that's a negative skew of your data. So here you can see that neither of these data sets are following a bell-shaped curve. And this time you would describe your continuous variable as either skewed or non-parametric. So understanding the shape of the data then determines how you treat it going forwards. So how you then describe the data and how you test the data if you want to carry out some statistical tests. When we're summarising continuous data, we're thinking about two things. First of all, we're thinking about the location of the data. And then we're also thinking about the spread of the data. And I'll talk about both those in a bit more detail so you can understand what I mean. Measures of central location. So for this, you're thinking about where is the data centered? What's your sort of average values within that data set? And this is summarized using either a mean or a median value. For a mean value, what you're doing is you're adding up all the values in your sample and you're dividing it by the total of number of people in your sample. So for example, if you wanted a mean age of everyone who was taking part in this workshop, you would add up everyone's age and divide it by the number of people within who were attending, and that would give you the mean value. So it's quite an intuitive statistic. Median, on the other hand, what you would do for this is that you would take all our ages and you would place them in order, starting with the youngest, whether that's 20 years of age, and working up to the oldest. And then once you've got the ages in order, you take the middle value. So if you only had 11 people in your data set and you ordered their ages, the median value would be the age of the person in sixth place. So that's the median value. It's the middle value in your data set. And if we think about measures of central location, how they're influenced by the distribution of the data set, you can see that on this middle graph, when you've got a nice bell-shaped curve, your mean and your median exactly align. They're in the same place. And on these graphs, we've also got the mode value, which is just the most common value in the data set. So it's where your graph peaks. So when you've got parametric data, your mean and your median align with each other. When you've got negatively skewed data, what you find is that your mean value is influenced by these higher values in the tail, and the tail pulls your mean value away from the center of your data. So if you were trying to pick the center of that data set, you can see that the median is probably a better representation than the mean. And the same with positively skewed data as well. You can see again that the median looks like it's usefully in the middle of the data, whereas the mean has been pulled away from the centre of the data by this tail in the plot. So what that means really is that when the data is normally distributed, we could use either the mean or the median. But the mean has, because it's a parametric value, it has properties that make it more useful than a median value, particularly when it comes to statistical tests. Testing for a difference in means between two groups, you'll have higher power than testing for a difference between two medians. So where you have the choice, you would choose the mean and you would report that. So the mean is used when your data is normally distributed. When the data is skewed, we've shown that the mean is influenced by extreme values and isn't a good representation of the central location of your data. And so the median is most commonly reported as the average value. As well as thinking about where the data is located, we also need to think about the spread of the data. So if we're looking at the mean age in two groups of data, that's useful. We might have two samples where the mean age is 20 in both of them. But in one sample, the ages might go from 0 to 40. And in one sample, the ages might go from 18 to 22. And they would both have the same mean value of 20. So we also need to think about the spread of the data. And that would, you can see that a data set that goes from 0 to 40 has a much greater spread than one that just goes from ages 18 to 22. When we report a mean, we would usually then report the spread of the data using a standard deviation. And what this is doing is looking at each of your data points, so each of the people in your sample, and measuring the average distance of their value from the mean of the data set. So standard deviation, don't worry too much about the equation there, but it's just giving you some idea, some indication of the spread of the data. And a data set that has a larger standard deviation has a greater spread than a data set that has a smaller standard deviation. When we report a median, we would also include a range or an interquartile range to indicate the spread of the data. For the range, what we're doing there is we're taking the maximum and minimum values in your data set. So if we go back to the example of age within a group of people, if the youngest person is 20 and the oldest person is 80, then that's your range. 80 minus 20, so it's 60 years of age is your range. But the range can be influenced by extreme values. So in a data set where the majority of people are between 20 and 40, but we have one person who's 80 years of age, the range doesn't give a very good idea of the spread of the data. Because most people are between the ages of 20 and 40, and it's only one outlier that's would make the range look much larger. So it's better to report the interquartile range to represent the spread. And what you're doing for this is finding the middle 50% of your data. So as with the median, where you put your sample values in order, for your variable of interest. The median is the middle value of your sample, and the interquartile range, what you're doing is then going a quarter of the way into the data set to identify your lower quartile, and then 3/4 of the way into your data set to find your upper quartile. So really you're putting your data set in order, and then you're splitting it into 4 and identifying the people at each of these 3 points to represent your median, lower quartile and upper quartile numbers. And this is better than the range because it's not affected by extreme values. So here we have an example of how we might present that data. So we've got a group of 110 males and 105 females. The first variable we've looked at is categorical, it's ethnicity, and we've reported the number and the percent who fall within each group. So we can see that for males, about 71% were white, and for females, about 62% were white. So that's really informative. For age, we've done a frequency distribution, and we've seen that this is skewed non-parametric data. And we've reported a median for the central location and an interquartile range for the spread. And it's convention to report the interquartile range in brackets with a comma between the lower and the upper quartile values. Systolic blood pressure has also been reported in the two groups, and this time when the frequency plot was looked at, we can see that the data was normally distributed. So this time we've chosen to report the mean and the standard deviation. And you can see the mean is slightly higher in males compared to females, and the spread of the data as well is also slightly higher in males compared to females. So you end up with a nice summary of the data by following those steps to decide how to present it. When it comes to carrying out research, what we're really interested in is the effects or the statistics of a population. So we might be interested in the risk between cardiovascular disease and type 2 diabetes in the population of the United Kingdom. But it's never feasible to look at a whole population with your research question. You're always going to be relying on taking a sample and using that sample to carry out tests or summarize your data, and then from those results you make inferences about the population. So you use your sample to decide if there is a significant association between different risk factors at a population level, and with the results from that sample, you're able to infer what you think is happening at the population level. So at the population level, if you could look at the whole population, you'd know the true value, the true relationship that was going on. With the sample, you're making a best guess. You're collating results from a sample to decide if you think there is something going on at the population level. So with populations and samples, there's always going to be the issue that because you're randomly selecting a sample, you can't expect it to give you exact results for what's happening at the population. There's always going to be some sort of uncertainty or random error involved. So here we can see that the blue represents what's happening in the whole population, so they're the true values. But when we've taken a sample, we can see that the sample population is shifted slightly to the left. So you wouldn't expect that from a sample you'd get the exact results of what's happening in the population. And this is called sampling error. So you can imagine that if you took repeated samples from the same population and all these samples were the same size, you wouldn't be likely to get the same result every time, because every time you select a sample, you're selecting slightly different people. You might by chance get slightly older people in one sample or more females in one sample. And those differences are going to mean that you end up with slightly different results between your samples. So there's always going to be some sort of variability. and this is referred to as sampling error. Often this sort of variability, this uncertainty around your estimates from your sample is quantified with a standard error, and it's also commonly quantified with confidence intervals, which are calculated using this standard error. So this standard error is some sort of measure of your sampling error. It's the uncertainty around your sample result. When it comes to confidence intervals, this is really telling you about the level of uncertainty around the measure of your effect. So if you get a really tight confidence interval around your sample estimate, that's telling you don't have very much uncertainty around your results. But if you have a wide confidence interval, that's indicative of a lot of uncertainty around your sampling result. This isn't quite statistically correct, but a confidence interval can informally be interpreted as the range of values that your 95% confidence contains the true population value of interest. So what you're doing when you're estimating some sort of risk or parameter from your sample, really that's just your best guess of what's happening in the whole population. And the 95% confidence interval gives you the range that you're pretty confident the true underlying value in the population lies between. So if we think of just trying to explain that in a bit more detail and think about how sample size might affect the confidence interval. Here we've got an example where we were looking at the risk of developing cardiovascular disease in people with and without diabetes. So do people with diabetes have a higher risk of developing cardiovascular disease? The study was carried out with 100 individuals and a relative risk was found of 1.89. So this has been estimated from a sample, and this is our best guess as to what the true underlying value is in the population, in the whole population. We're also, we've looked at quantified the error around our result, and we've decided that we're 95% certain that the true underlying value in the population lies somewhere between 1.29 and 2.49. So 1.89 is our best guess, but we're pretty certain that the true value in the population lies somewhere between 1.29 and 2.49. And that was a study with just 100 individuals. If the same study had been done, but this time with 1,000 individuals, we can see that the relative risk is 1.89, but this time the confidence interval has narrowed. It goes from 1.49 to 2.19. And that makes sense because with a larger sample size, we're now more certain about our result of 1.89. We've reduced our uncertainty because you can imagine a study with just 100 patients, you're going to have more uncertainty there than when you've got a larger sample size. And when the sample size is increased even further to 10,000, we can see that the confidence interval narrows even further. So we've got even more certainty around our result. So what I'm trying to indicate here really is that sample size, as sample size increases, the random variation and the uncertainty of your results decrease. And I think this is quite intuitive. You can imagine that where you've got a study with just 10 individuals, you're not going to be that confident with your result. Whereas if you've got a study with thousands, then you're intuitively much more confident with your results from that study. But to get to that point where you've got a statistic and a confidence interval or a p-value that you're interpreting, you need to think about your setting up a hypothesis test for your research question. How you do this is that you'd usually define your null and your research hypothesis, sometimes called your alternative hypotheses. You check that you got the right level of significance for your study. You collect relevant data from a sample of your population. So you find your random sample and you collect data to analyze from them. And then you use that data that you've collected to carry out some sort of test. We'll talk a bit later on about the types of tests, how you select the right tests and which tests are appropriate for which type of data. But it's the same for all tests, in that you will use that test to calculate a test statistic and a corresponding p-value. And that p-value then helps you interpret your results. So if you think about the null and the alternative hypothesis first, so the null hypothesis is always going to be the hypothesis that says there's no effect or no association in the population of interest. Whereas your alternative hypothesis is that there is an effect, there is a significant relationship or association between different risk factors or a difference between different groups. So if you think of an example, here our null hypothesis is that the incidence of heart attack is the same in men and women in the population. And our alternative hypothesis is that heart attack incidence is different in men and women in the population. So you can see the null hypothesis, usually denoted by H and 0, is that there's no difference, and the alternative is that there is a difference. More often than not, we do a two-sided test to test every hypothesis. So with a two-sided test, what you're saying is that the difference could go in any direction. So our alternative hypothesis is that the incidence of heart attack is different in men and women in the population, and this could go either way. So it might be that men have a greater incidence than women, or women have a greater incidence than men. To test this, we would do a two-sided test. There is an alternative though, which is doing a one-sided test. And this time, instead of our alternative hypotheses being that there's a difference, this time we're saying that incidence of heart attack is higher in men compared to women. So we're only allowing the difference to occur in one direction. The one-sided tests are quite unusual. I think I would always recommend doing two-sided tests because it's very difficult to know for certain that and to argue when your work is being peer reviewed, you would have to be able to convincingly argue that the relationship could only go in one direction to justify having a one-sided test. One-sided tests are less conservative than two-sided, so you're more likely to find a significant result with a one-sided test, and that's why it's probably more appropriate to always do a two-sided test and to err on the side of caution. To decide whether there's a significant difference or a significant association or not, what we do is we carry out the test and we get the result as a p-value, and we see if the p-value is below or above the significance level that we've set. The level of significance by convention is usually set as 0.05, and So for this, what we're saying really is that we're allowing for a 5% risk of concluding that a significant difference exists when there is no actual difference. So because you're taking a random sample from your population, there's always a chance that you're either going to conclude that there's a significant difference when in fact there isn't one, or you might miss a significant difference when in fact there is one. And this is because you're not looking at the whole population. So you're only making a best guess at what you think is happening, which means you could make a mistake. So with the p-values, if you set the p-value as 0.05, a p-value less than 0.05 from your test is telling you that the probability of obtaining your study results or something more extreme, if the null hypothesis is true, is very small. So the probability of seeing the results you have in your sample, if the null hypothesis is true, is really small, and therefore you think, oh, it's so unlikely that I would have seen these results if the null hypothesis is true. I'm going to reject the null hypotheses. So a p-value less than 0.05 means you've got unusual results if the null hypothesis is true, and so you reject it and conclude that there's a statistically significant difference at the 5% level. If your p-value is greater than 0.05, that means it's not really that unusual that you've seen your results if the null hypothesis is true. You know, the probability of seeing your results if the null hypothesis is true is greater than 5%, and therefore you sort of say, well, our results seem to support the null hypotheses, so we won't reject it at this point in time. It's useful to consider, especially when it comes to interpreting confidence intervals, which I'll show you in a minute, null values when it comes to statistics from research questions. So a null value is an estimate that shows no difference between groups. So for a difference, the null value is always going to be 0. So for example, if we think about systolic blood pressure in men over 70, we've taken a sample and we've found that the average, the mean value was 120. And then we've done the same in a group of women, and we've also found that the mean systolic blood pressure is 120. So the mean difference between the two groups is just 120 minus 120, which is 0. So for a difference, hopefully you can see that really, that's really quite straightforward, that when you're looking at a difference, the null value, the value that shows no difference between two groups, is 0. This differs when it comes to a ratio. So when you're carrying out health research, there's lots of ratios appear in your results. There's incident rate ratios, risk ratios, odds ratios, hazard ratios, and these are all ways of looking at the risk of an event in one group compared to the risk of an event in another group. So here, for example, we're thinking about the risk of gestational diabetes in white pregnant women, and we've assessed 100 pregnant women, and we found that 16 had gestational diabetes. So the risk of GDM in white pregnant women was found to be 0.16. We also looked at 100 black pregnant women, and again we found that 16 out of 100 had GDM. So here the risk of GDM is also 0.16. Now, when we calculate the risk ratio to compare the risk in one group by the other, what we're doing is dividing the risk in one group by the risk in the other. So instead of mean difference, where you're minusing one value from another, now you're dividing. So you can see here that the risk ratio to compare risk of GDM in the two groups, is 0.16 divided by 0.16, which equals 1. So for any sort of ratio, because you're dividing the value in one group by the value in another group, the null value is always 1. So null value for a difference is 0, null value for a ratio is 1. And this is really useful when it comes to interpreting 95% confidence intervals, because it allows you to look at a confidence interval and see if there's a statistically significant difference or risk or association by seeing by looking at the limits of the confidence interval. So here we've gone back to the example where we've looked at the risk of developing cardiovascular disease in people with and without diabetes. And our observed result in our sample was our best guess of the risk was 1.89, which shows an increased risk of CVD in people with diabetes compared to those who don't have diabetes. And the 95% confidence interval for this went from 1.29 to 2.49. So we can look at that confidence interval and think about whether that's showing a statistically significant result or not. Because if you remember, the confidence interval was telling us what we thought the possible plausible values for the true underlying value in the population were. So here we're saying from our sample, our best guess of the risk ratio is 1.89, but we believe we're 95% certain that the true underlying value in the population lies somewhere between 1.29 and 2.49. So what you need to look for really is whether this confidence interval includes the null value. I've already shown that the null value for a ratio is 1, and you can see that 1 is not included in this confidence interval. So if we're 95% certain that the true underlying population value is somewhere between 1.29 and 2.49, this means we don't think that the true value can be 1. So we don't think that the true value could show no difference between the two groups. And therefore, our confidence interval is telling us that we think there is a statistically significant difference, because we think that the null value isn't a possible plausible value for the risk ratio. So what the confidence interval doing is that it's allowing you to assess the statistical significance of a result, and the confidence interval and the p-value are always going to agree. So if your null value is inside the 95% confidence interval, then your p-value is going to be greater than 0.05. So when you carry out the statistical test, your p-value will be greater than 0.05. That's associated with your statistic and the confidence interval. And when your null hypothesis value is outside the 95% confidence interval, then your p-value will be less than 0.05. So they're always going to agree. So here we have an example just to sort of exemplify that a bit more. So here we have the odds of developing lung cancer in smokers compared to non-smokers. The odds ratio was found to be 2.59 from our sample, with an estimated 95% confidence interval going from 2.10 to 3.08. So here we can see that the confidence interval shows a statistically significant difference, as it doesn't contain the null value of 1. We don't think 1 is a plausible value for the odds ratio. And the p-value agrees. This is less than 0.05, so it is also showing a statistically significant association between smoking and lung cancer. And here we have an example for a difference. So this time we're looking at HbA1c levels, And we've found that there was a difference of 0.24% between South Asians and whites, with it being higher in the South Asians. And the 95% confidence interval around this estimate went from 0.16 to 0.33. So this time, because we're looking at a difference, the null value is 0. And the confidence interval shows a statistically significant difference in HbA1c levels between South Asians and whites, as it doesn't contain the null value as 0. And the p-value agrees because it's really small. It's a lot smaller than 0.05. So both by looking at the confidence interval and the p-value, you would conclude that there's a statistically significant association between ethnicity and HbA1c levels. So just to summarise confidence intervals, because they're really useful to consider when you're reading the research literature and when you're producing results. An informal way of thinking about the 95% confidence interval is to consider it to be the range in which you are 95% sure that the true population value lies. Your 95% confidence interval is going to be wider in samples where there's greater variation in the population values, and also when your sample is smaller. So a larger sample size results in a narrower confidence interval because you're reducing the uncertainty in your results. And a confidence interval is an estimate of the precision of your observed values in the sample. So finally, if we think a little bit about choosing the right statistical test, there's a number of things to think about. First of all, you need to think about whether you're comparing two groups for a difference, or whether you're looking at some sort of correlation or association between two continuous variables. So, for example, is blood pressure different between males and females, or is blood pressure correlated with age? As age increases, does average blood pressure increase? You need to think about the type of data that you're looking at. Is it nominal, ordinal, interval, ratio? So, whether it's categorical or continuous, and then whether what type of data is within that. And then you also need to think about the design of your study. So has the design of your study led to your data being paired or unpaired in terms of the measurements? And I'm going to explain that a little bit more. So what do I mean by paired data? So paired data is where you're comparing data between two groups, but every value in one group is paired in some way with the value in the second group. So, for example, you might be looking at systolic blood pressure before and after exercise. So you have one value in an individual taken before exercise and one value afterwards. So you can see there your data is paired because each of the before measurements is paired with the measurement that was taken in the same person after exercise. Systolic blood pressure in males versus females. So now you've got two different groups. This is unpaired data. You can't pair the data from every male with every female. Grip strength in the right versus left. I should have put hands there. That would be paired if you've taken one measurement in a right hand and one measurement in a left hand in a number of individuals, then that data is paired. So there's a few more examples there. For the unpaired data, so where you have different people in your two groups that you're comparing, sometimes the only time that would be paired rather than unpaired is if you match the two groups. So sometimes to try and make sure your groups are balanced in terms of age or other factors such as ethnicity, sometimes you match them. So if, for example, you're comparing a group of individuals with type 2 diabetes and a group of individuals without, what you might do is for every person you include in your study who has type 2 diabetes, you might match them with someone without diabetes who has similar characteristics. So you might, for every person with type 2 diabetes, you might select someone without diabetes who's the same age, ethnicity, and sex. And that would lead you to having paired data, because each control in that case, even though it's a different person, has been matched with one of the cases in terms of their characteristics. And then using all this information allows you to choose the statistical test that's appropriate for the data that you have. And a nice way to do that is to use something like this here. There's quite a few different ones on the internet, which is a flow chart that leads you through a number of different criteria and helps you decide which test you need to do. And each of these tests, when carried out, is going to give you a p-value that you can then interpret and see if there's a statistically significant difference between your groups or some association. I'm not going to talk you through all the tests, but if we sort of think through a few examples. So for example, if we are looking for a difference in blood pressure between two groups, maybe one group who has type 2 diabetes and one group who doesn't. First of all, we know we're looking for a difference rather than a relationship because we've got two groups that we're comparing. Blood pressure we know is continuous rather than ordinal or nominal, so that takes us to here. We could look at the shape of our data and decide if blood pressure is parametric. Let's say, yes, it is. So we come to here. We're comparing unpaired data, so people with and without diabetes, and they haven't been matched. So we've got unpaired data. And we're just comparing two groups, people with and without diabetes. So that leads us to do an unpaired t-test. So that's one way to sort of think about your data, and it leads you through to the test that you need to do. If we think about a relationship, so for example, if we're going to look at the relationship between, let's say, blood pressure and age, blood pressure, we know it's continuous data. I guess for ordinal, we might be looking at something like sometimes pain is measured on a scale of 0 to 5. So you have ordered data that you want to compare against maybe something like age. So it's a relationship, so that would take you down that route. But if we keep thinking about blood pressure, because it's continuous, and if it's normally distributed blood pressure, we would do the Pearson correlation test, or we could do a linear regression. If it's not normally distributed, then we do the non-parametric version of the correlation test, which is Spearman's rank. So this is just a really useful way to look at your data and think about the type of tests you need to do to look for a statistically significant difference or association between different variables. So I think I'm going to end there. Hopefully that's given you a really nice overview of biostatistics, and it's giving you a bit to think about for your projects. Thank you.